except marginalization, the and letters. The period JML or reset this semester and part.
Facing
Hello everyone. Welcome to our deep dive podcast, where today we'll be reviewing the paper titled On Multi-Token Prediction for Efficient LLM Inference. Are you ready to explore the world of multi-token prediction, or MTP, in large language models?
Absolutely. This is a fascinating topic, especially as LLMs become more central to AI applications. To start, can you explain what multi-token prediction actually means in the context of LLMs?
Of course. Traditionally, large language models are trained for next token prediction, or NTP. That means, given a sequence of tokens, the model predicts the next token, one at a time, in an autoregressive manner. But MTP aims to predict multiple tokens in parallel, which could significantly speed up inference.
That sounds promising. So instead of generating one token at a time, the model could generate, say, two or more tokens at once, right?
Exactly. This approach can reduce the sequential bottleneck in LLM inference. The paper investigates whether models trained for NTP inherently possess MTP capabilities, and how we might adapt or enhance these models for better MTP performance.
Interesting. Before we get into the technical details, why is this important? What's the motivation behind accelerating LLM inference with MTP?
Great question. As LLMs grow in size and complexity, inference becomes slower and more resource-intensive. The sequential nature of NTP means each token depends on the previous one, which limits parallelization. MTP could allow for faster generation, making LLMs more practical for real-time applications.
That makes sense. So, what are the main contributions of this paper?
The authors make several key contributions. First, they show that LLMs trained for NTP already have some MTP capabilities, though these are data-dependent and improve with model size. Second, they explore the challenges of adding MTP heads to frozen LLMs and find that the hidden layers are highly specialized for NTP, making adaptation difficult. Third, they experiment with joint training strategies for MTP heads and the backbone, which improves performance but doesn't fully close the gap with the baseline.
That's a lot to unpack. Let's start with the first point. How do LLMs trained for NTP exhibit MTP capabilities?
The authors use a technique called numerical marginalization over intermediate token probabilities. Essentially, they calculate the probability of a sequence of tokens by summing over all possible intermediate tokens. This is computationally expensive, but it shows that NTP models can, in principle, perform MTP.
Can you give an example of how this marginalization works?
Sure. Suppose you want to predict two tokens ahead, given a context. You'd calculate the probability of the first token, then for each possible first token, calculate the probability of the second token and sum over all possibilities. Mathematically, it's a sum over the vocabulary for each intermediate token.
That sounds like it could get out of hand quickly, especially with large vocabularies.
Exactly. That's why, in practice, they limit the sum to the top 0.99 of the predicted probability distribution, which makes it more tractable.
So, what did they find when they applied this method to different model sizes?
They found that larger models have better MTP capabilities. This is because larger models tend to be more confident in their predictions, concentrating probability mass on fewer tokens, which simplifies the marginalization process.
That's fascinating. Does the type of data matter for MTP performance?
Yes, it does. The paper shows that MTP performance is strongly data-dependent. For example, in translation tasks, where the context reduces ambiguity, MTP works better than in open-ended generation.
That's logical. If the context is more deterministic, the model can make more accurate multi-token predictions. Now, let's talk about the second contribution, adding MTP heads to frozen LLMs. What challenges did the authors encounter?
The main challenge is that the hidden layers of pre-trained LLMs are highly specialized for NTP. When you attach new MTP heads to a frozen backbone, The heads struggle to adapt because the intermediate representations have already discarded information that might be useful for MTP.
How did the authors measure this specialization?
They use the Kullback-Leibler KL divergence between the token probabilities predicted by intermediate layers and the final output layer. In large models, the intermediate layers quickly converge to the final output, indicating strong specialization for NTP.
So, simply adding MTP heads isn't enough. What about joint training strategies?
The authors experimented with several joint training strategies. They trained the MTP heads together with the backbone, sometimes using techniques like differential learning rates, head warm-up, and weighted hidden states.
Can you explain what these strategies involve?
Sure, differential learning rates mean training the heads with a higher learning rate than the backbone to help them adapt faster. Head warm-up involves training the heads with a frozen backbone before joint training. Weighted hidden states involve taking a weighted sum of all intermediate hidden states as input to the heads, rather than just the final output.
Which strategy worked best?
The combination of weighted hidden states and differential learning rates achieved the best MTP performance among the tested strategies. However, even with these improvements, there was still a significant performance gap compared to the baseline established by marginalization.
That's a bit disappointing, but also insightful. It suggests that the NTP specialization is a tough barrier to overcome. Did the authors suggest any future directions?
Yes, they did. They propose further exploration of weighted hidden states, experimenting with different initialization and normalization schemes, and possibly increasing the number of layers used for MTP adaptation. They also suggest that full MTP pre-training might be necessary for the strongest performance.
Let's talk a bit about the experimental setup. What datasets did they use?
Most experiments were conducted on the IWSLT 2017 translation dataset, specifically the German to English direction. They also used open-ended generation tasks with reference generations from GPT-4o.
How did they evaluate MTP performance?
They used top 5 accuracy for next token and second token predictions. For marginalization experiments, they calculated the actual next token probabilities and estimated second token probabilities. For MTP models, they used the probability distributions output by each head.
What about the training details? Were there any notable choices?
All trainings were performed for one epoch using cross-entropy loss, with a batch size of 64 and a cosine annealing learning rate scheduler. They used the Atom W optimizer with weight decay, and learning rates were set to half the pre-training rate for each model.
Did they use any parameter-efficient fine-tuning methods?
Yes, they used LoRa, or low-rank adaptation, for fine-tuning the backbone. LoRa adapters of rank 8 were applied to all query, key, and value layers.
That's a popular method for efficient adaptation. Now, let's discuss the architecture for MTP. How did they design the MTP heads?
Instead of attaching additional heads on top of the pre-trained LLM, they replicated the final transformer layer n times to create n independent heads. Each head processes the final hidden state from the shared backbone and applies a shared unembedding layer to compute token probabilities.
Why use a shared unembedding layer?
Using a shared unembedding saves significant resources, both in memory and computation, since these matrices are large. It also allows the matrix to be fixed during training, reducing the number of trainable parameters.
That's efficient. Did they compare their architecture to other approaches?
Yes, they compared it to Medusa, which attaches additional linear heads with their own unembedding matrices. The authors argue that their approach is more resource efficient and allows the heads to attend to previous tokens in the sequence.
What about the weighted hidden states approach? How does that work?
Instead of using the final output of the backbone as input to each head, they take a weighted sum of all intermediate hidden states. Each head learns its own weight vector, which is normalized before taking the weighted sum. This aims to leverage information from earlier layers before specialization.
Did this approach help?
Yes, it improved MTP performance, especially when combined with differential learning rates. However, the performance gap with the marginalization baseline remained.
Let's talk about the results. How did the different strategies compare in terms of top 5 accuracy?
The baseline, which used marginalization, achieved the highest accuracy for both next token and second token predictions. Training only the heads, with the backbone frozen, resulted in lower accuracy. Joint fine-tuning improved performance, and the best results were obtained with weighted hidden states and differential learning rates.
So, the main takeaway is that while adaptation is possible, it's challenging to match the performance of the baseline. Is that correct?
Yes, that's correct. The strong specialization for NTP in pre-trained LLMs makes it difficult to amortize MTP capabilities with additional heads. Marginalization remains the most effective, though computationally expensive, approach.
Did the authors discuss why larger models perform better at MTP?
They did. Larger models tend to have more selective, or sparse, next token probability distributions. This means the model is more confident in its predictions, which simplifies the marginalization process and improves MTP performance.
That's an important insight. As models get bigger, they become more deterministic, which helps with MTP. Now, what are the practical implications of this research?
The findings suggest that while MTP adaptation is challenging, it can still be useful in scenarios where only rough token drafts are needed, such as self-speculative decoding. For the highest accuracy, full MTP pre-training may be necessary.
Are there any recommendations for future research?
Yes, the authors recommend using marginalization-based approaches as a baseline for future work. They also suggest further exploration of weighted hidden states and multi-layer MTP adaptation.
That's a comprehensive review. Before we wrap up, can you summarize the key points of the paper?
Certainly. The paper shows that LLMs trained for next token prediction inherently possess some multi-token prediction capabilities, especially as model size increases. However, adapting these models for efficient MTP via additional heads is challenging due to strong NTP specialization. Joint training strategies and weighted hidden states can improve performance, but a significant gap remains compared to the marginalization baseline. The research highlights the need for further work in this area, especially for applications requiring fast and accurate multi-token generation.
Thank you for that summary. This has been a deep and insightful discussion on multi-token prediction in LLMs. Any final thoughts?
Just that as LLMs continue to evolve, efficient inference will become increasingly important. MTP is a promising direction, and this paper provides valuable insights and a solid foundation for future research.
I agree. Thanks to everyone for listening. We hope you enjoyed this in-depth review of multi-token prediction for efficient LLM inference. Stay tuned for our next episode, where we'll explore more cutting-edge research in AI.
Goodbye, everyone.
Goodbye.